University of Oregon. His work is in the area of landscape ecology, and he's talking about anticipating surprise. So, Bart.
Thank you. And this is the forward button?
It is.
Okay, thank you. Well, thank you. Glad to be here today. Landscape planners and designers typically, oh, I'm sorry. This is not the right slide. Can we somehow, there we go. Thank you. Now I'll start. Landscape designers and planners typically derive a single best solution for every problem. But global change is proceeding at a rate and pace that forces human societies to face conditions unlike those ever experienced before. Looking toward the future reveals key uncertainties about climate change impacts and people's responses that make it impossible to identify the best solution to many problems. So, confronted with unprecedented circumstances related to deep uncertainty, risks, and trade-offs, how do we navigate between being overly cautious and being heedless? Rather than trying to make our predictions exactly right, perhaps we should aim for useful approximations of the boundaries of uncertainty and bracket plausible ranges of variability in how climate, ecosystems, and people may jointly influence the future. Our approach thus allows users to explore large numbers of potential future landscapes so as to iteratively test initially simplistic solutions and revise them into more informed plans of actions. I focus on one slice of a very complex model, wildfire. The Willamette Valley is a complex mosaic of land uses and fuels that includes extensive areas of rural settlement embedded within a mixture of agricultural, successional grassland, and forest. But despite our extremely high fuel loads and dry summers, we haven't had the explosive wildfires that have occurred in much of the U.S. West because our summer droughts aren't as deep and long. But what if the fuels in the Willamette Valley met the hot, dry summers of California? How might this interact with a doubling of the human population that's projected in the next 50 years? Can biodiversity conservation help protect homes? What might happen should people with very little experience with wildfire encounter a novel and rapidly changing fire regime? Specifically, we ask three interrelated questions that form the basis of a suite of contrasting alternative future scenarios of how the future might unfold under different assumptions and planning approaches. If you will, a set of what-if stories about the future based on climate change impact, uncertainty and variability in land use planning, and different ways that people might approach fire hazard management. We used a model, an agent-based model of landscape change called Envision, that has at its core a human decision model. Agents occupy each landscape unit, are presented with choices about what actions they may take on the landscape. They change their behavior over time in response to feedbacks from the landscape and interactions with other agents. We're investigating an 80,000 hectare study area around the Eugene, Springfield, Oregon metropolitan area, 16,500 tax lots divided into 79,000 integrated decision units. We used a survey of over 1,000 rural landowners to populate the initial landscape with diverse types of landowners, each with different values and goals that affect how they manage their lands. Might say that this current landscape has about 7,000 people in it, half of them in 3 small towns. Under some projections then, we may get as many as a tripling or a quadrupling of rural populations in this landscape. So we modified Envision to substantially incorporate mechanistically and empirically validated models of population growth, vegetation succession, and wildfire under the influence of future climate. And we constructed model linkages that allow us to explore specific interactions and feedbacks among these processes. To the extent possible, we simulate all the processes with our best science and the best realism we can muster. We constructed an analytical framework organized across 3 scenario dimensions related to our 3 questions. So we see on the, if I can point here, low versus high climate change being driven by monthly climate data from the Muroc general circulation model and the Hadley general circulation model. Compact versus dispersed development. Compact representing a continuation of Oregon's very strong statewide land use planning laws that constrain urban development, and a dispersed development scenario modeled on recent ballot initiatives that dramatically relax those standards. Finally, across this other dimension, we have what we call conventional fuels management, basically density thinning. Thin the trees, reduce the surface fuels. And we compare that to what we call our mixed biodiversity treatment that instead emphasizes the restoration of oak savanna and oak woodland, imperiled historic ecosystems that appear to be quite well suited to future climate. If you look then across, we can look at individual scenarios that vary only in one dimension, or we can look across each dimension as a whole. So here's some quick results. This is surprise. Here's a graphic representation of uncertainty. It shows the total area burned by wildfire each year in over 600 model runs, arranged roughly by the 50-year total of fire burned from front to back. Note that each peak that gets into the green shows a fire with over 6,000 hectares burned, typically driven by a single large fire. We classify these fires as surprising because they're larger than anything on record in comparable areas of the Willamette Valley. With this in mind, then, let's untangle that pretty wide diversity in what types of surprise and what types of future we might see. First, I'm going to show you a spatial and temporal reconstruction of events just across the surface of how the landscape is changing, not looking at the mechanistic processes underneath. But we're going to look at how population growth and actors' decisions influence where rural houses happen. We're looking at how actors' management influences vegetation, how vegetation and succession interact with wildfire, and then how wildfire influences population growth and threatens dwelling units. I'm going to set this simulation running just to get things moving. This is about a 10-mile by 10-mile area. It's about 230 square kilometers you're seeing there. On the left, you see densities of rural houses growing slowly over time because it's a compact scenario. On the middle, you see agents implementing treatment blocks. Fire hazard, conventional fire hazard treatments in the red, oak restoration in different colors, and it seems to have stopped. Excuse me. Sorry about that. Interesting. We just tested this. Oh, these are the simulations we worked on for about a month. There we go. Okay, you're seeing people change their minds there. Under the influence, as treatments expire, people are changing their minds based on feedbacks from the landscape. And then finally, you're seeing vegetation change, slowly sometimes due to succession, quickly due to timber harvest, wildfire, changes of losses of agricultural land in the landscape. But let's freeze it at year 37, and you're going to see a large fire. It's an 8,000 hectare fire we simulated, and I want to see you what's happening under the hood with this mechanistic flame map fire model we're using. You see the fire spreading over the course of a day. On the right-hand side, you see that as the perimeter expands, it leaves behind it black and gray areas. The black are standard-placing fires that have killed all trees. The gray are lower-intensity fires that have not changed the vegetation state that much. On the right, then, as the fire expands, and this is weirdly not simulating, these are the things you really hope you can avoid. There we go. I'm not going to touch it. I'm staying away from the thing for a moment. As the fire goes, you see the dwelling unit areas there that are in orange were threatened by the wildfire, either because it was a standard placing fire or because it was a surface fire, but they hadn't had defensible space around the home, and those are all choices they make. In the middle, oh boy, isn't this fun? Sorry. Well, in the middle, what you can see then is actually look how the treatment effects slow and change the spread of fire as it moves around them. To my knowledge, we're the only engine-based model that has used a mechanistic fire model like this in its simulations of fire perimeters. Moving along. So, looking under the hood then, some of the lessons we've learned. Under the historical period, this is a representation of days with extreme fire weather and the total expected area burned. If you look under the Merit projections, not much changes. You see actually the number of days with extreme fire weather decreases. There's an upturn in the total amount of area burned, purely driven by increased ignitions because of population growth. Under the Hadley scenario, all hell breaks loose, if I may say so, and it happens quickly. This is across 200 model runs, but those bars there are the number of fires over 6,000 hectares that occurred in the model at different times. So this is a composite sense over many, many simulations of what the future might look like, but it still doesn't explain why. The first question, I think, is what would it be like to be living in one of those futures, not standing here at 8,000 feet looking across all. If you lived in this future, this shows the area of the largest fire in the study area over time. You'd have time to prepare. Fires are getting gradually larger. The agents have time to prepare, change their behavior for the wildfire. But look what happens there. This is 2015, a projected fire under the Hadley climate stream that explodes from out of nowhere, giving people no time, no warning of this coming. If we look across all those futures, we can begin to disentangle the types of scenarios and conditions that lead to different probabilities and likelihoods of fire and why they're happening. If we fully expand our data set, we have 2.5 billion lines of data, which we can reconstruct every event that happened in the landscape and why over time. So it's a powerful analytical tool. Some of the last comments here, this just shows the 50-year fire footprint under the Muroc and the Hadley scenarios. Very, very different. Well, if you wind up living in the Muroc scenario, if you invest in the conventional fuel scenario, our agents spend $20 million over 50 years to thin trees for fires that never come. And there's no ecological benefit to it in particular. On the other hand, if you wind up being in the Hadley world there, the conventional scenario does substantially better in protecting homes. It's not because the restoration treatments don't protect homes. Homes are 3 times more likely to escape a fire in the oak savanna grasslands because they're so easy to defend space around. But what happens is the restoration treatments cost more money. We have budget caps in here, and so less area in the landscape gets treated. And the quick-moving grassland fires move safely through those homes and then hit these untreated treated parts of the landscape and blow up into explosive fires, threatening many homes. So there are dilemmas, right? What do? We don't know which is going to occur. How do we go forward? I'd say neither of our initial solutions is the right one. But as we iteratively work through this, we can begin to craft different solutions that address those specific problems we found in the model. I want to wind up with a couple comments. One about education. I've been teaching this in landscape planning studios now. We train students to use the software, and they learn different things. They have a model that talks back to them, and they get addicted to it because they think of a plan they think they can idealistically achieve each of those different values, 12 different great things to do in the landscape, and suddenly there are trade-offs. You can't achieve them all. And they find out about probabilistically and risk in ways that most planning tools we use don't provide for them. Finally, just wrapping it up, some key thoughts. The lessons for anticipating surprise to me are about exploring the dimensions of surprise, untangling the what, when, where, how, and why of simulated landscape change using analytical tools that allow us to reconstruct every event in the landscape and why it happens, an ecologist's dream. It may be a simulated world, but I can tell you exactly what happens and why if I'm willing to wade through the data. It exposes key challenges. For example, the tensions between waiting for clear trends to emerge versus proactively acting before crisis occurs. It brings focus to the links between actions, uncertainty, risks, and trade-offs associated with the different planning approaches. And I've come to think of the model less as a problem solver than a problem generator that leads you from simplistic initial solutions toward more sophisticated understandings. It helps you think probabilistically rather than deterministically about trajectories of change in large landscapes over long periods of time. Is it going to help catalyze action? That remains to be seen. But our goal is to make the model simpler, easily, more portable, to take it into both more post-secondary education and actually into secondary education with underserved communities and help people start to think about their future in the landscape differently over time and see if we can help catalyze action. So, thank you very much.